So in this talk, I'll be discussing another approach to programming for GPUs and CPUs, and this is a set of languages that have been developed in the last few years. Um, so this these languages are generally referred to as performance portable languages, and for large applications, HPC application developers really can't afford to write a custom version for every piece of hardware that comes around. And maintaining it is quite difficult. So having a single source for an application code is really a necessity for these kinds of applications. The Department of Energy has been actively sponsoring conferences and workshops on the topic. And two of the popular performance portable productive languages in the Department of Energy are Raja and Kokkos. They both are for C++. Raja is more modular in structure. It has separate components for compute and data management, and it was designed to be more adaptable for how an application team implements it in their code. And this was because the different Lawrence Livermore application development teams wanted to be able to customize it a little bit for their programming style. Kokkos is the other one, and that's from Sandia National Labs. And it has more of a comprehensive approach, which fits more within the Sandia type of development strategies. And they are also actively migrating parts of what they're developing into the C++ standard. Kokkos and Raja are working somewhat together in concept. They're building off of what they learn from each other. So they're in many ways quite similar. They're both great choices. And they're both supported for AMD GPUs, and we have staff supporting both of them. We have one staff member working pretty aggressively on optimizing some of the Raja kernels, and we have several people working with Kokkos. I'll be talking mostly about Kokkos here. Raja is similar, but I don't have time to discuss both of them in detail, so we'll spend most of our time on Kokkos. And why Kokkos? Oh, and I do want to mention, we call this performance portable, but it's performance portable for C++. If you're using multiple languages such as Fortran, C, and C++, we really, the languages we talked about earlier today may be more suited for that. So, portability for C++ doesn't necessarily mean portability across HPC languages such as the Fortran C and C++ languages. So for C++ applications, Kokkos is a very attractive option. It provides a single source capability. And so using Kokkos with a different backend, you can generate code that will run with OpenMP CPU loop threading, or you could generate code which will run on NVIDIA GPUs or AMD GPUs. And they even are working on backends for the Intel GPUs. So the idea here is that you have a single source that you maintain, and Kokkos is handling the backend to generate it for the different types of hardware. Now, why Kokkos on this? Well, really, if you look at the differences in the code for HIP and OpenMP and what we'll see here, they're not really greatly different in their basic structure of what they're doing. They're moving data to the GPU, computing on the GPU, and a compiler could do this for us. But it's going to take a while for compilers to be developed that can do that kind of code generation. And so the advantage, Kokkos is a really heavily templated library and header files. So you can develop that quicker. It's portable across all the different systems. And that makes it something that we can deploy quickly. Kokkos is well supported and it's been around 10 years, so it's fairly mature at this point. Since it's being used in many critical applications at Sandia National Laboratories, they are committed to keeping that development going. And we're seeing a lot of use worldwide at this point. We've seen it in some of the hackathons. We've done it in Europe. It has exascale computing funding in the United States, and so they've been able to keep that development going and generate some pretty good documentation and training materials. And what we find with Kokkos is quite often the generated code from with Kokkos, it performs nearly as well or better than lower level languages. Now, one of the disadvantages is you've got a couple abstraction layers that are separating you from your source code and what's actually happening on the GPU. So that can uh, that can give you a little bit more effort at trying to understand what's happening between those different layers. But it's well worth it for the savings uh, in maintaining the code and developing the code. So the HIP backend has been around for quite a while. They actually had it working on some of the commodity GPUs at an early date. And so Kokkos will generate code for both the AMD CPUs and the GPUs. And they've been aggressively developing their implementation with the rollout of Frontier and other systems. They have been right at the forefront of getting everything working. And this last fall, they promoted the HIP backend to production status. It has been working for a while, but they, with these new systems, they're putting more emphasis on it. And it handles many of the unique attributes of the AMD GPUs, so you don't have to worry about it. You don't have to know quite as much about how the GPUs are working for the AMD specific attributes. So Kokkos is a Greek word. It means grain, seed, or kernels. And it's basically a library based on C++ templates. They're quicker to implement and distribute, so they can get it portable across multiple systems, whereas if we waited for the GCC compiler, the LLVM compiler suite, it would take far longer for that to get to a mature state. And eventually we do think that many of these things for GPU programming will be migrated into the language standards, but that can take even longer than the compilers. I do want to note that the multi-dimensional array concepts from Kokkos will be in the C++23 standard. And this is the first time, I mean, we've been talking about multi-dimensional arrays in C and C++ for years, And finally, we're seeing actual capability within those languages. There's a team of computer scientists at Sandia National Laboratory that developed this tool. And originally it was for their mathematical solvers that they have for their applications. They wanted an abstraction layer because maintaining separate code bases is just not tractable. And it supports the OpenMP threading, CUDA, HIP, and others. So to get a handle on what's going on with Kokkos, let's look at the high level concept. And this is true on any of our highly parallel architectures. So including CPUs. So you got basically two basic requirements, and I hope you're sort of seeing that high level pattern across all these languages. And you have execution capability. So we've had one approach to making loops fine-grained parallel. So fine-grained parallel means that we're using shared memory and splitting the loop across threads, processes, or some other on-node compute capability. So we need to be able to execute that and tell it to run on the target architecture. Generally, we think of this as loops, but it can also mean single lines of computation. And then the other aspect is memory handling. So we have to allocate memory, move memory, give the memory different attributes. And so memory handling is the second requirement that we have in any programming language for GPUs. And so Kokkos must have those two components to be able to be portable across all these different languages and architectures. So let's look at the kind of abstractions that are available in Kokkos. So they have something they call execution spaces, and that defines the compute hardware where these computations are done. There's three patterns that are needed: parallel for, parallel reduce, and parallel scan. A parallel for is a simple do or for loop. Parallel reduce is something like a sum across an array. Parallel scan is where each process or thread needs to know its starting and ending indexes. So a parallel scan will add up all the values of the processes below it. So that may say process 4 knows it needs a starting address of 410 because the rest of those values are done on the first sets of processes. So those are the three things that are needed in any to handle any execution pattern. Not all of our languages have all three of these. Some of them don't have parallel scan, and you have to hand code how to handle that. But having this execution pattern makes it much simpler for the application developer. Execution policies. So what is the index set that we need to operate on? And then team policies. So grouping threads into teams. Is it in, does this team have a shared scratch space that it can use? Or is it distributed across multiple work groups? So these team policies can help us optimize for different types of computing hardware. And then we have memory spaces. And so how is the data laid out? What are the traits? Are we going to have atomic access? Are we going to be doing random access rather than contiguous access? So there's two ways to build Kokkos for your application, and these are both supported through CMake. Kokkos is very aggressive at integrating CMake into their system. And so an external build, you can build the back end and then link to it. That can be a very effective way to develop code. But there's also an inline build where you make it part of your source code through a submodule, for example, with Git submodule. And then you can build it at the same time as your application. This can be convenient if you're switching between different backends on the fly. You can make sure your application and the Kokkos library are built with the same support, device support. So that's one of the decisions you need to make. I actually, in this presentation, I show both versions of it. So we've got two examples, the stream triad. We're going to use the external build of Kokkos for that, and then a shallow water simulation code. These slides really go through how to do this. It's also in the HackMD for the stream triad. And these are for general systems. So I have not tested it on the Cray platform. There may be some slight differences that you might need for the Cray system. One of the advantages of, let's say, Kokkos is you could do this on your laptop or your workstation and use the OpenMP backend and do a lot of your code development with that. And then you should only have small changes needed to run on a GPU. So here we're going to do an external Kokkos build with an OpenMP backend. You can also do the HIP backend, and then we're going to change our CMake file to add the Kokkos headers and arrays. We'll do the memory allocation and the execution pattern, the parallel fours. We'll add Kokkos timers, and then we'll run our application. And so you've got fairly well-defined set of steps to convert over to using Kokkos. Now, Raja has a separate memory package from their execution language. So it's a little easier to migrate existing code using Raja, and it's more adaptable for particular applications, but it's still very similar. So once we have this done, we can then build for the AMD GPUs. We can build for the CUDA GPUs or the NVIDIA GPUs using the CUDA backend. So we can, and then we can run on the CPUs. So with one set of code, we can run across all of the platforms we're interested in. So we first start out, we'll get the Kokkos from GitHub. We'll go ahead and make a build directory, and then we'll execute the CMake command. And you can refer to the Kokkos documentation for the current set of options to this CMake command. So here we're enabling serial. So we're going to have a serial capability. We're going to enable OpenMP. So this is going to be OpenMP threading on the CPU. And then it's just simply make install. Sorry, I'm struggling with the annotations. Okay, we're just not going to worry too much. I'll see if I can get it here. So to build with the HIP backend, we just have to add slightly different options. So we're going to do enable. We're going to do enable we're going to enable HIP on, and we're going to turn on the Zen architecture. And this one is building for Vega 90. So this is a commodity-based GPU for AMD. And then we're going to use the HIP-CC compiler. So once we do this and build, then we can point to that package and use that in our application. Okay, so we can go into our CMake, and by putting in find package Kokkos required, we can then link with the Kokkos package that we're pointing to. So here's the stream triad. You can download it from some of the examples I've created. This is from chapter 13 of my book. If you go into this version, it has both the original code and the modified code for each of these steps. You go in, run CMake, you should be able to run the code at this point. So the next step is we can add Kokkos views for our memory allocation. We have to add the Kokkos header file. We have to add and initialize and finalize. You get sort of an odd message if you don't do this, because it doesn't free up some of the resources at the end of your program. Sometimes it's just a warning, but occasionally it will actually cause an error. So you'll always need this with any time you're using Kokkos. You need this initialize, and you need to bracket the code, from the initialization to the finalize. So we're going to replace those static array declarations with these Kokkos views. So Kokkos view double, and we're going to allocate A, B, and C. So we can do that, and we can run. Now, if you're on the GPU, this will not run properly, because we're going to try to execute, and we need the data on the GPU, and it's still on the CPU. So our next step is to, or I got that backwards. So our next step is to, we'll do the execution of the loop. So just to summarize here in Kokkos, we have this requirement to have the header file, to initialize and finalize, and we need to have the scope guards, the braces around the code that we're going to have in Kokkos. Okay, and here are memory views. We can declare the array using this syntax Kokkos double colon view, and then you can access 1D data with either x square bracket I or x parentheses I. Now, when we get to 2D, we have to use the parentheses form. Kokkos does deallocate automatically, and it does initialize the data. There is an option to tell it not to initialize data. And this can be important for things like OpenMP, where we want to make sure that our first touch is putting the data where we want it. You can have an unmanaged view of a pointer. So we have the XView array, and we want to bring it, or XRaw array, and we want an XView, which is our Kokkos handle for that data. to give us a view of a XRAW array that was allocated with a system call, with a regular malloc call or a new. So let's move on to the execution pattern. So it's a parallel for. You just replace the for loop with a parallel for. And this has been a concept. This is telling us that we want to do fine-grained parallelism on this loop. And on the GPU, it will do the execution on the GPU if we're working in that execution space. So you need the parallel for, and then you need to have at the end of the loop, you need the brace and parentheses and a semicolon. So this is fine-grained parallelism. We've had many projects that have looked at creating different for alls, for eaches, a lot of different syntax to indicate it. Kokkos uses this parallel underscore for. And then we rebuild and run. It will run here, but Kokkos suggests adding these environment variables to tell the OpenMP runtime where to run. And you can do this and see what kind of speed up you get with OpenMP on your CPU. So right now we're developing code which should run everywhere, but we're testing it on the CPU. Now our last step is to add Kokkos timers. So there are timers in the code, but if we add the Kokkos calls, we don't need our separate timer routines. So here's basically what our code looks like for the stream triad. We have our timer call. We have our initialize with the open brace. We have our memory allocation, and we have our parallel for. So this parallel for is for the initialization of the data. And then we have the parallel for our stream triad. And then we do a finalize, and there'll be a little bit more on the next slide well, no, I guess I got it all. I think there is a little bit more for timers. No, maybe I got it all on here. It's always nice when you can get the whole code on one place. So you can then run these, with the serial version. You can run it with OpenMP, and you can compare the runtime. To find out how many virtual cores you have on your CPU, you can do an lscpu or look at /proc/CPU info. And so this is our first step in sort of assessing what our parallelism is doing for us. Okay, now we can do a little bit of portability exercise. We can build the same stream triad with HIP. We're going to do that export of the Kokkos dir to point to our HIP version of Kokkos, and we can run our code and measure the performance. Then we can do the same thing with CUDA. And so we can compare serial, OpenMP, AMD GPU, and NVIDIA GPU, all with the same single source. So Kokkos also has built in some performance profiling, and these are linked into the AMD profiling tools we'll talk about on Friday. So you can build the Kokkos tools. You can run your application with these tools. I'm not going to go over these in detail. You can refer to these when you get to wanting to look at the performance of your code. But basically, you're getting a submodule within the Kokkos GitHub for Kokkos tools, and you do a make on it. There's most of it's header, but there are some that has to be some parts that need to be compiled. And then you run your application with that tool. You can also use the environment variable to point to those Kokkos tools if you want your paths to be a little simpler. And then you print out the results of your tool with this KP reader command. So just to review, we talked about how to build the Kokkos software as an external build. We added the Kokkos dependency in the CMake. We initialized and finalized Kokkos. We converted the arrays to Kokkos views, and then we added the parallel for syntax to execute the loops in parallel. Okay, so I'm going to briefly go over the shallow water application. It shows a little bit more complex use of Kokkos. So the steps are similar. There's some tricks in here that we will get into. We now have a parallel reduce. We need to swap views, and that can be difficult in some languages, but you know, it can be really important because it reduces it's a big optimization for codes. And then we're going to go ahead and do our portability study. So to get this, we get the examples from chapter 13 and go to the shallow water example. Now, I'm showing you the steps to convert the original code to each of these parallel versions. But all the conversions are done there if you just want to go to the answers. So you can do a build of there's a script that will build the code, and you build HIP, CUDA, OpenMP, or serial version. And then so you're going to have one in a separate directory for each of these versions. And then the Kokkos version will be built for that execution space, whether it's an NVIDIA GPU, an AMD GPU, or on your CPU. So inline build, we're going to do a git submodule add down in our source code. So usually at, probably the top level. And then you check out the version of Kokkos you want to use. We usually pin the version of Kokkos so that, we don't get updates without knowing that Kokkos has changed. And then we modify the CMake list much like we did before. So we're going to add that subdirectory Kokkos. And then we're going to add something to the link line. For the initialization, it's still the same steps. We're going to add the header file and the initialize, finalize. And then we're going to change our mallocs to Kokkos views. So we had a malloc 2D. Now we're going to do a view on a 2D array. And so we do, there's a couple things I want to note here. So this is just a descriptor for the array, so we know what it's called. That helps especially when you're debugging. You got two dimensions, and it's a double star array of view. And then we can remove the freeze. That will be done automatically. We have to change, this is probably the most complex part, is that we have to change the indexing for all the arrays to from the standard C++ approach to what really looks like Fortran. And this is done partly because it generates less index calculations, and that can give us an efficiency on the GPU by using this form. And so that's what has gone into the standard as well. And then here we are changing the swap pointer to explicit loops. That's going to generate extra copy of those arrays at this point, which we will deal with later. But that'll actually slow down the code at this point because of that additional memory movement. Okay, so since we're 2D, we have to use the parentheses syntax. We can control the data layout with this layout left or layout right. Layout left is Fortran ordering and layout right is CC++ ordering. And Kokkos was designed by default to switch the layout on the CPU and the GPU. So it automatically does that. So CUDA space is layout left. So these two lines are equivalent. But you can experiment with that to see if your data layout is backwards. So we need to talk a little bit about this index set, or what is called the MD multidimensional array range policy. So we define a range policy here. So we see that range policy here that we're going to include in our parallel 4. So the first case is for 2D. You see that we have a line continuation. You can also create an object for that MD range policy and then use it within the parallel 4 if you prefer that style. But we're going to execute this, and we've got rank 2 in this case, so we have a 2-dimensional loop. And lambda, haven't talked a lot about this, but Kokkos uses it can use actually 2 different representations, but it generally uses a lambda concept in C++, and so it's going to bring in these variables into the lambda generic loop concept. So that's being imported from the space where this is being executed. And this basically handles the syntax for the lambda, whether you need it on the CPU or the GPU. So it's it does it correctly for what you need to work on the GPU. Okay, so here we're introducing the parallel reduce call. So we have a sum reduction, and to do that, we're going to do a parallel reduce. We're going to call it a sum original mass, so that that helps us in the debugging if we use the debugging tools, or in the profiling. It will label it with that name. And so we introduce the range policy, and it's a little trickier because we have this variable and this variable are separate. So each thread, if we're on the CPU, is going to do a local sum. And then at the end, across the threads, it's going to sum into this original total mass variable. So there's 2 levels of sum that are happening here. Similar for the min, although we don't, we have a special function there that needs to be executed for mins. So both of these are parallel reduces. And so those are the general patterns you get with reduction calls in Kokkos. So let's summarize. We can do a parallel reduction of a 1D array. We need that local variable for the local sum, and then we need a result variable, x sum in this case. For the 2D, it's very similar, although now we have a range policy for two dimensions, and the minimum we just have a slightly different result syntax for the min function. Okay, so we can also swap pointers in Kokkos, which some of the languages don't really support this well. So here we're replacing that copy of old to new. We're going to do a swap pointer. We have to declare this temp view, and so simply using that macro, we can swap the pointers here, and that will restore our performance that we lost when we did the copy. See a lot of chatter going on in the chat, but I can't follow it. So just a couple concepts that we need to make sure that we understand is Kokkos does a shallow copy by default. So it just assigns the pointer for the view. So it doesn't actually copy the data in the array. If we want to do a deep copy, we have to specifically ask for it. So there's a deep copy call in Kokkos that you can do that. And again, we can run and compare the versions. We can see, what the performance is with the different versions and across the different architectures. So we note that, when we did that serial and we introduced the copy from new to old, that actually almost doubled our runtime because basically we had to load all that data into memory again and copy it to another array. And so that's expensive. And when we get to that point where we swap the pointers back, we regain that performance. So you can profile with you can build the Kokkos tools and profile with them as before. And this is the kind of output you get from that KP reader. So it shows the different routines, how long they took, the total execution time, and it's in it's in kind of a summary array that makes it a little easier to understand what's going on. It's not a detailed profile. It's more of a high level profile. So we learned how to handle multi-dimensional arrays here. We saw how to do reductions with parallel reduce with both sum and minimum, and we saw how to swap view pointers. And so that's the end of that presentation. Okay, Michael, you got a question?